Okay, so in the first place, this is what we have today. All right, so let's kill this two things. One, two, as 1 over dx, 1 over x plus xy, y minus xy. So in this integration, we realize that we have xy, which is the the conflicting aspect of the integral. So we are going to break it down together for us to be able to understand it well. Okay, without wasting time, let's see the ball rolling, and then we'll see the best way to go about this integral. Okay, all right. Now let's open the page. Okay, then we'll set the ball rolling. The question says, the integral 1 over 1 plus xy into bracket 1 minus s squared dx. Okay, this is the question we have been given to tackle. So let's see the best way to go about this. First and foremost, the xy is the issue. So what we can do is to use some kind of substitution to solve this. If we say we want to use maybe sine or anything like that, I think that would do. So in the first place, let's say if we have let's say let our x to equals the sine of angle theta. Okay, sine of angle theta. So if that is the case, then we'll say that the differential of that will give us cos theta d theta. Okay, so that you see we can use this one as a substitution. Well, if this changes, meaning the limit that we're given is in the question, the limit that we were given was 1 to 0. 1 to 0. So if it's 1 to 0 is the limit, then when x is 1, our limit will be theta will be sine inverse of 1, and that will give us pi on 2. Also, when x is 0, our theta will be sine inverse of 0, and that will be 0. So the limit straight on changes. Okay, and when we look at the denominator, which is 1 plus xy of the integration given, so our integration is 1 plus xy as the denominator. When we put a sine theta, this one will be 1 plus y sine theta. Okay, then as we also saw that we have square root of 1 minus s squared. Okay, this also when we substitute the sign, we're going to get square root of 1 minus sine square theta. Okay, so that will be the square root of that. Okay, and we know that this is the same as saying that this is cos square theta. Okay, therefore eventually that is what we are going to have. All right, so let's substitute all those ones back into the integral. So our integral that we saw earlier is given as the integral. So 1, 0. Then it becomes 1, 1, 0, which we know it to be 1 over x plus xy into bracket 1 minus s squared dx now will be equals to pi on 2, 0, all over 1 plus y sine of theta into bracket minus square root of cos squared theta. Okay, dx, as we know, it will be cos theta d theta. Okay, so that is what we have, and this we can further simplify this down here as pi on 2. Let me use different color that makes it more distinctive. So pi on 2, 0, cos theta d theta all over 1 plus y sine theta into bracket multiply by the square root of cos squared theta will be cos theta. So straight on, we know that the cos theta will take care of the other one. So this one will cancel this. So then our final integral will be pi on 2, okay, 0 d theta all over 1 plus y sine theta. So this is the integration then that we have to tackle. Okay, so what comes into mind? Because you see, we have 1 plus y sine theta d theta. So if we look at this very carefully, we can break it down by saying that let's substitute the theta here. Let's say let z to be equals to tan theta over 2. And so if that's the case, when we square that, we square both sides, we are going to get tan squared theta over 2. Alright, so tan squared theta over 2, tan squared theta over 2, it's so beautiful because tan squared theta over 2 will help us to be able to do wonders, because we know that in a real life, tan squared theta is given as is given as sec squared theta minus 1. So our tan squared theta over 2 is given as sec squared theta minus 1. Okay, so in this wise, we can make sec squared theta the subject, so that our sec squared theta will be equals to 1 plus tan squared theta over 2. Okay, now we know that if this can also be written as 1 plus z squared. Okay, so z squared theta, okay, can be written like that. Z squared theta over 2. So let's put this one aside, okay, and we delve deeper. Okay, now we have the theta over there, but we should bear in mind that since we have the theta over there and we have z also, z to be equals to tan squared theta over 2, when we differentiate this, we are going to get dz to be equals to half sec squared theta over 2. Okay, the theta. Okay, so with this one, we can also use it as a substituent. Okay, so look at this one so that our integration will be easier for us to manipulate. Okay, once again, this one we can multiply through by 2, so this one will be 2 dz is equals to sec squared theta over 2 d theta. because we have gotten rid of the half. And we know that sec square theta, okay, sec square theta, we know our sec square theta is 1 over cos square theta over 2. So if that is the case, when we substitute this into the equation, then we are going to get 2 dz, yeah, 1 over cos square theta over 2 d theta. Okay, then we can take care of the theta. So our d theta will be equals to 2 cos squared theta over 2 dz, yeah, dz. Yeah, because that's what we see. We have 1 sec square theta. When we differentiate the tan square theta, that's what we got. So 1 over cos square theta, as we substituted, that's what we have got. Yeah. So what do we do? We can do something wonderful. We can do something wonderful. So we have to do our substitutions. But also bear in mind that we have in the equation, if we look at it very carefully, you see here, we have sine theta over here. So we have to find a certain substitution that will help us. Okay, so let's see, z square theta, we say z equals to tan square theta, and when we did, we have dz to be equals to half sec square theta d theta. Okay, now let's make proper expression. Okay, so we have cos coco, that cancel that, we have this at tan theta over 2. Now if we look at it very carefully, then you see our cos square theta can help us to do a certain kind of substitution. Yeah, so let's do that substitution and see. So dz, initially we said let z to be equal to tan theta. Okay, so over 2. So we have to do a certain substitution. Let also, because of the sign, because of this sign over here, because of the sign, because of this sine theta over here, let's do a certain substitution. All right, so we will say that because of the sine theta, we know that for double angle formula, sine 2 theta is given as 2 sine theta cos theta. So that if we say we consider only sine theta, then this one will be 2 sine theta over 2 and cos theta over 2. So then we can substitute the respective values into the equation. Okay, so that our d theta, since we know everything, this one now becomes the theta. We don't want to jump steps, so this will be pi on 2. Let me use blue. I like blue, it's my color. Okay, so pi on 2 integral 0, Okay, and as we look at it, it's looking so beautiful. Okay, so pi onto the 0. So we have now our d theta all over 1 plus 2, 1 plus the 2. Yes, because of that, so this is 2 sine 2y sine theta over 2 and cos theta over 2 as 1. But when we substitute the theta, which we also know to be cos square theta d theta, that's what we're going to put in the equation. All right, cos square theta d theta. So this time we're going to use this cos square theta d theta, this one, into our the theta. So the theta is 2 cos square theta over 2. So the theta is cos square theta over 2. So we'll bring the 2 out. So it will be integral pi 0 pi on 2. Okay, then it's 2 cos square theta d theta. So 2 cos squared theta the 2 d theta. Okay, all here over the z. Sorry, the z will be that. So this will be the z. Since we made it the subject, so this one will be the z. dz all over 1 plus 2y sine theta over 2 cos theta over 2. Okay, we can break it further by since we have cos square theta here, we have sine over here. Okay, so when we divide through or we factorize, let's factorize cos square theta out of our integration. So then this integration will be into bracket. I'll bring the 2 out. So 2 out pi into pi over 2 0, and this is cos squared theta over 2 dz all over our expression 1 plus 2y sine theta over 2 and cos theta over 2. So we're going to factorize. So let's factorize cos square theta out. Factorize. Okay, cos square theta over 2 out. So this is a big assumption. Alright, so this will give us this. So we're going to have 2 out, nothing change again, pi on 2 0. Okay, and this will be dividing through by cos square theta. Okay, will be 2 out 1 over cos square theta over 2 plus 2y sine theta over 2 over cos theta over 2. Yeah. Okay. Further simplification will be again 2 out integral pi on 2 0. Okay, this will be the same as saying that we have 1 over sec square theta over 2 plus 2y tan theta over 2. Yeah, we're getting there. We're getting there. So, if this is the case, then we should remember, recap. We should recap that the earlier times we made some suggestions. We said we should let z to be equal to tan theta over 2. And because of that, when we square this and we have tan square theta over 2. And also, we had an expression that said that sec squared theta over 2 was equals to 1 plus z squared. Okay, if you remember this earlier, which we'll go back to it again, this and that. Okay, so now if you look at it, then when we substitute this into our integration, this and that, okay, our expression now will change. So the integration now will become 2 integral 1 0, because we have substituted the values earlier. So this will be the z all over, since we know sec squared theta to be that will be 1 plus z squared, okay, plus our 2y, and we know tan theta over 2 is z, so we put z here. So this becomes our new equation. This is a new challenge because our expression, the denominator that we are getting over here is z squared plus 2zy plus 1. That's a quadratic in z. But we have to do something so that we'll be able to integrate this, because I can see that it's approaching something like a tan inverse function. Okay, so because of that, we can say that this is we can say that z squared plus 2zy plus y squared minus y squared plus 1. Where y squared minus y squared plus squared, this is 0. 1 y squared minus y squared is 0. So further, we can expand this to be z plus y all squared minus y squared plus 1, which we can make it look very beautiful as z plus y all squared minus or plus 1 minus y squared. There, that's beautiful. Okay, so with this, we can put this one back into our integration now. So we can substitute this, all this one here. Okay, so that you see our final integral will be 2 out integral, okay, 1 0 dz is all over z plus y all squared plus 1 minus y squared, 1 minus y squared. Okay, you see it's coming. So, but let's make some assumption that can help us to compute this. I think we can let xi is equals to the z plus y that we have. If we say that, then the xi will be equals to dx, dz. Okay? If that is the case, then our limit will also change, because when when z is equals to 1, our z1 will be 1 plus y. Okay, and if z is equals to 0, this one will be 0 plus y, which is y. So the limit now has changed. So now let's substitute this, small introduction here into our integration. So we're going to substitute that back into the integration here. Okay, so now our integral, because we have done a substitution, is going to be 2 integral 1 plus y and y as our new limit. Then this one will be dz instead of dz all over z squared plus 1 minus y squared. 1 minus y squared. Okay, so this, we can do something about it. We can, if you look at it very carefully, since we have the squared here, okay, if we compare this one to the tan inverse integral, that says that if you have the integral 1 over s squared plus a squared, it's normally is given as 1 over root a tan inverse of x over root a. Okay, so if that is the case, then we have to do something for this one to resemble this. So this one to be able to resemble this. Okay, so let's see. From that, we can say that our integral, instead of, since we have xi squared over here, so we can say that 2 integral 1 plus y, this. Okay, now we have the xi. Okay, so we can say the xi n over xi squared plus square root of 1 minus y squared all squared at the up. So when we do that, yeah, then we're getting closer. Okay, so with this now looks like that. So that if the integral is of this form, okay, dx, okay, then we can use the tan inverse to integrate this. So finally, our integration becomes 2 integral 1 plus y, okay, with our xi equals all over xi squared plus square root 1 minus y squared, okay, all squared will be equals to, if we look at it, this one will give us 2, when we integrate it, start 1 minus y squared tan inverse of xi over square root of 1 minus y squared. Okay, so this will be the integration, but we shouldn't forget our limit. The limit is what? 1 plus y to y. So when we substitute the limit into the integral, we are going to get 2 all over 1 minus y squared tan inverse of 1 plus y over square root 1 minus y squared into bracket. That's the upper limit. So this is the upper limit minus the y, which is also going to give us 2 square roots of 1 minus y squared. Okay, the tan inverse of y, let me write it well. Tan inverse of y okay, so tan inverse of y, alright, then we come here, tan inverse of y into bracket y all over square root 1 minus y squared into bracket. Yeah, so we've put in all the limits into that, but we should know that since they are subtracting, this is subtracting this. Let me do edit, undo. Okay, so this is subtracting this from that. So we've integrated it. The rest is simplification. So when we do simplification, you all know that we can bring 2 over square root 1 minus y squared out of the equation. Okay, so we'll be dealing with tan inverse of 1 plus y over square root of 1 minus y squared minus tan inverse of y divided by 1 minus y squared. Okay, so this will be the integration final. But let's go back and recap. Okay, so what did we do? So right from the onset, there's a question given to us. All right, this is what we have. Okay, xy. And xy was the issue. Xy was the issue. So we substituted x to be sine theta, and we differentiated it to have cos theta d theta. Now because of that, the limit changed. So when we substituted it, the x equals to 1 and x equals to 0. Our limit we had was this and that. And also 1 plus xy became 1 plus 1 sine theta. Okay, that's 1 plus 1 sine theta. And 1 minus x squared, when we substituted the sine theta in, we have square root of cos squared theta. Then we substituted back into the integration, we had this. Okay, we simplified it, then we had 1, which is d theta plus d theta over 1 plus 1 sine theta. We made this assumption. We say let z go to be tan theta. So when we squared it, we have tan squared theta over 2. And we know this eventually got us here. Alright? Then we know z squared equals to tan squared theta. We know that when we differentiate even z, let me clean this one. Yes, when we differentiate that, we get z squared theta d theta. Okay, so eventually we did that, and we had d theta over 1 plus y sine theta. We know because of this sine theta over here, we have to break it down to be 2 sine theta cos theta. All right? Then we substituted that in. Then we also brought 2 cos square theta d theta in there. We simplified and we got to this eventually. Then we factorize cos square theta over 2 into our equation. Okay? After further expansion, we had 1 over sec square theta plus 2y tan theta. Then we know for sure that this sec square theta is equal to 1 plus z squared, as we saw earlier. And this tan theta is z. So when we substituted into the equation, we had this. And straightforward, we realized that this very one, we had this is a polynomial. Our denominator was polynomial. You see, this was polynomial. So we simplify the polynomial to this, and we had z plus y squared plus 1 minus y squared. We substituted back into our denominator, and we have this. Then we say let z equals to z plus y. Then we differentiate it, and then we change the limit to this, and our equation now became this. Now, looking at this integration, this is squared, and 1 minus y squared. Okay, so we see that if this, we assume this one to be the a squared, and this one to be the s squared. Okay, then we are going to get 1 over a tan inverse of x over a. So we did the same thing. So because of that, you see, we have to, instead of y minus y squared here, instead of y minus y squared, okay, we made it all into bracket 1 minus y squared, the square root of that. Then we squared it, which come back to the same. And when we look at this, you see, our integral, okay, became this. So we have 2, when we integrated it, we had 2 1 minus y squared tan inverse of that. Then we did our further substitution, and we have that. But friends, I'm going to leave this one with you. I will like to give this one to you as an assignment. If you integrate this one and simplify it further, you will get cos inverse of y all over square root of 1 minus y squared. Try your hand on and let me see whether you can get it right. Yeah, then we can talk further. Nice. Please subscribe and ring the bell as well, so that you'll be the first person to receive other notifications. Well, that is what the time will bring us up to. I will leave the last part with you guys for you to try your hand on and simplify this for me. Bye.